Welcome to 25th lecture of course Polymer Science and Technology. In today's lecture we will see the viscoelasticity. In the term viscoelasticity you can see it is made up of two terms, visco and elasticity. Elasticity, as all of you know, it's defined by the Hooke's law of elasticity, and it says that if any object is deformed within the elastic limit, on the removal of the load it will regain its original shape. Okay, and the formula for elastic deformation is sigma is equal to capital E gamma, where gamma is the strain and capital E is the modulus and sigma is the longitudinal stress. There is a different notation for different stresses. In case of shear stresses we will be using term tau, but for longitudinal stresses like tension or compression we will use the term sigma. Okay, so this formula says sigma is equal to capital E gamma. Gamma is the shear, sorry, gamma is the strain which is having no unit. Okay, now let us consider spring, because spring is considered as a elastic element. It is completely elastic in nature. Let's say the original length of the spring is capital L, and when P load is applied on the free end of this spring will deform and there will be delta L increment in the length of the spring. So the strain is the increase in the length divided by the original length, defined as delta L over capital L. Okay, so this is the strain in the spring, and once load is removed, this increment in length delta L is regained and original shape is achieved, capital L. So this is the elastic element. Elastic element, upon the application of the load it will deform, and upon removal of the load it will completely regain its original shape. So this is the definition of an elastic element. And what is the definition of a viscous element or visco element? Visco element is governed by the Newton's law of viscosity, which says that the shear stress is directly proportional to shear strain rate. Here you mind it that here in case of Newton's law of viscosity we are using term shear strain rate. This dot represents the rate, whereas in case of Hooke's law of elasticity it's just a strain, not the rate of strain. So according to Newton's law of viscosity, shear stress is proportional to shear strain rate, and a proportional constant is the viscosity. And a dash pot represents the viscous element. Dash pot, you must have seen a kind of plunger and barrel system where the plunger can move upward and downward inside the barrel. So once the plunger is moved upon the application of load, and upon removal of load it will not come back on its own. It will regain its it will retain its deformation. So this is a dash pot model. So what we can do, we can plot the deformation versus time curve. Let's say at time t is equal to 0, at the origin of this curve we have applied certain load to the free end of the dash pot. Then what will happen? The dash pot will keep on increasing its length, and this increment in the length will continue unless load is removed. Once the load is removed at this point, then dash pot will stop increasing its length, but it will not regain its original length, and all the deformation caused by the load will be as it is. You can see now it's a constant value of the deformation. It is not going to achieve its original value. It is not going to come on the x-axis, this curve. So this type of deformation is known as time delayed deformation, where deformation is taking place with respect to time. higher the time, greater will be the deformation for the constant load. In comparison to dashpot, let us see the behavior of a spring. Again, we'll plot a deformation versus time curve, and let's say at time t is equal to 0, we are applying, at that point of time, we are applying the load P to the free end of the spring. Then what will happen with the application of the load, spring will suddenly expand, and delta L will be the expansion. So this much deformation is delta L deformation. Then it will not increase, or it will not undergo further deformation, and the deformation will be constant as long as applied load is present. Let's say at time t is equal to t, at this point of time we have removed the applied load P. Once we will remove this applied load P, then immediately spring will retain its original shape, and the deformation, means delta L value, will come to the 0. That means this curve will come back to the x-axis. So this is the behavior of a spring, and this is the behavior of a dashpot. Now you might ask why I am giving the example of spring and a dashpot. So reason is that spring represents a complete elastic element and dashpot represents a complete viscous element. And our material, polymer, is a viscoelastic material. Viscoelastic materials means it shows the property of the viscous fluid as well as it shows the property of completely elastic material. Okay, so it is a hybrid type of a material that exhibit the property of both the cases, viscous element as well as the elastic element. Okay. Now you might ask question, why polymer behave like this? So reason is that the viscous part which is non-recoverable deformation part is because of the presence of the intermolecular bonding of the chain. What are the intermolecular bonding? Intermolecular bondings are the hydrogen bonds, dipole attraction, and in case of some pure hydrocarbons such as polyethylene, polypropylene, van der Waals forces. Strongest secondary bonding is the dipole interaction, then hydrogen bonding, and the weakest is the van der Waals attraction. Okay, so at least one of them is present in any kind of polymer. So the viscous behavior of polymer is contributed by the intermolecular secondary attraction or interaction among the chain, and these interaction may be deformed when polymer is loaded. Hydrogen bond may break, dipole attraction may break, van der Waals forces may also be overcome. So intermolecular attraction can be overcome during the loading of the polymer. Okay, and when the chain will pass over each other at the new location, new secondary bonds can be formed. Now the elastic part of the polymer comes from the crystalline region, because crystals, in case of crystalline or semi-crystalline polymer, the crystalline region behaves like a elastic element. When they will be deformed, they will when load is applied, they will be deformed up to some extent, and when load is removed, they will regain its original shape. As well as in case of extreme stretching, when all the molecules, all the polymer chain have been aligned in the direction of the stretching, then chains are open up, and now any further pull or the load P, if is applied on the polymer, it will try to stretch the primary bonding, the covalent bonding between the carbon-carbon atoms or in the backbone chain of the polymer. You know, the primary bonds are much stronger than secondary bonds, because the bond energy for the primary bond is of the order of 80 to 90 or sometime 100 or more than 100 kilojoules per mole, depending upon the types of bond, whether it's carbon-carbon single bond or carbon-carbon double bond or carbon-carbon triple bond. So it is in the range of almost 90 to 100 kilojoule per mole, whereas the secondary bonding, which is responsible for the viscous behavior of the polymer, is of the order of few kilojoules. You can say from 2 to 3, 4 kilojoules per mole is the bond energy. So primary bonds are much stronger, and when primary bonds, covalent bonds, they are stretched in the direction of the pull, they basically, the bond length has to increase to accommodate this pull or push force. So when bond length is deformed, it's very difficult. Lot of energy is required to pull apart the atoms in the backbone chain. So it's very difficult to distort the bond length of polymer or any molecule. So the energy is absorbed in the material in terms of the very slight increment in the bond length, and just upon the removal of the load the polymer or the molecule is will basically retain its original bond length, and in that course of action the length of the polymer which has got increased because of the stretching delta L will come back to its original length L. Okay, so this is the explanation how the elastic part and the viscous part of the polymer are contributed by the primary and secondary bondings. One thing, and second thing, you have to keep it in mind that there is nothing like a spring or a dashpot inside the polymer. If you try to search a dashpot or a spring inside the structure of the polymer by zooming inside the polymer using some scanning electron microscope, you are not going to find any dashpot or a spring present over there. The representation of spring and dashpot is just to understand the phenomena of the intermolecular attraction, secondary bonding, and the elastic part because of the stretch in the bond length of the primary bonding. So as such, there is neither spring nor a dashpot present inside the polymer, but its primary bonding and secondary bonding which is going to be deformed during the stretching is responsible for this behavior. So in order to understand the viscoelasticity, we will be using dashpot and a spring for our understanding point of view, and you have to keep it in mind that there is no as such spring or dashpot inside the polymer. Okay. Now the first viscoelastic model is the Maxwell model. In the Maxwell model, it's based on the name of the scientist Maxwell. He said that the behavior of the polymer chain is like that if a spring and a dashpot is connected in the series and load P is applied. So he said that when dashpot and spring is connected in the series, then it will represent a behavior of polymer chain. Okay, so you must understand that the increment in the bond length is basically defined by the elastic element, and deformation due to secondary bonding, deformation of the secondary bonds is defined by the dashpot. Okay. Now let's say that the modulus or the spring constant is capital E and the viscosity of the dashpot is eta. Okay, and we are applying a load P. Here you have to understand that the P symbol is for the load. Load means force. Unit will be Newton. It is not a pressure. Pressure has got unit Newton per meter square. So here we are talking about load. Load is a force and force is having unit Newton. So upon applying load P, sigma S is the stress developed in the elastic element and sigma D is the stress developed in the dashpot. Since both the elements are connected in the series, then these two stresses are going to be same. In series, sigma S is equal to sigma D. It's very much similar to an electrical circuit that the current passing through two resistors connected in the series will be same. Okay, so this is the stress which is connecting, which is present in these two elements. It is going to be the same. Okay, now let us plot the deformation versus time plot, and for this Maxwell model, let's say at the time t is equal to 0, I am applying my load P, and within no time load is being increased from 0 to value P. Then it is retained for certain duration of time t. Then after t time it is being removed. So once load is removed, it will come back to x-axis or the 0 value. Correspondingly, the deformation in the entire models means the spring and the dashpot connected in the series. So once the load is applied, what will happen? The spring will deform immediately within no time, and this deformation is known as the elastic deformation, which is very quick and it takes no time to deform, because once the load is applied, the bond stretching will take place in fraction of a second, means you can say within no time, and when load is removed, again the bond length will retain its original value within no time. So the elastic deformation is immediate. It is not going to take some time. It's immediate. That's why this line is completely vertical. In no time it will attain certain value of the deformation. Then this dashpot which is connecting in the series will start deforming at the same time at some particular rate. You can see that this straight line at some angle, this angle will basically define the rate of deformation. So dashpot will keep on deforming, and this deformation will be known as the viscous deformation. Why? Because dashpot is representing the viscous element, and dashpot will keep on deforming unless we remove the load. Let's say at this time is equal to t, we have removed the load and load has come back to the 0 value at that particular point of time. So what will happen? Whatever elastic deformation that was caused by the stretching of the bond angle, it will immediately retain by the model. But whatever deformation that was caused by the viscous deformation of the dashpot will not be regained, and it will remain present. So this difference, you can see this vertical difference of the curve shows no viscous recovery in the dashpot. So mathematically we know that the stress in the spring is a elastic element. It follows the Hooke's law of elasticity. So stress is equal to modulus multiplied by the strain in the spring. and the viscous element is the dash pot. So stress in the dash pot sigma d is equal to the viscosity of the dash pot, which is eta or eta d multiplied by gamma dot d, where gamma dot d is the shear strain rate in the dash pot. So these are my two governing equation, and at equilibrium we have already seen in my equation here that sigma s is equal to sigma d. So we can say this is the sigma stress in the spring is equal to stress in the dash pot, and the strain, which is a function of time. Why strain is function of time here? Because in our model this strain, or which is governed by the deformation, depends upon the time of the application of the load. As long as load is applied, this deformation will keep on increasing. Once load is removed, then deformation will stop. So strain is a function of time t, and the total strain in the model is equal to the strain in the spring plus strain in the dash pot. Okay, so we can differentiate this equation with respect to time. So d gamma over dt will be d gamma s over dt plus d gamma d over dt. Okay, and here you can see that this d gamma d over dt is nothing but the shear strain rate, because we are doing the differentiation of the shear strain. So it will become shear strain rate. So this right hand side is d by dt. Instead of gamma s, I can write sigma s over capital ES from my equation number 1. Here sigma gamma s will be equal to sigma s over ES. So I have written, instead of gamma s, sigma s over ES, and this is my gamma dot. So from equation number 2, gamma dot d is equal to sigma d over eta d. Since sigma d is sigma, so I can write it sigma d over eta d, and since sigma is equal to sigma s is equal to sigma d, so this equation is going to be d gamma over dt. Since modulus is a constant value, so I can take out the modulus out. So it is 1 upon ES d sigma by dt plus sigma. Instead of writing d, since it is same, I can write sigma over eta d. So this is my final Maxwell equation. We can also write this equation in this term. Instead of writing d gamma over dt, I can write gamma dot. So this is the strain rate. Strain rate in the Maxwell model is equal to ES, this is 1 over ES, and d sigma over dt is stress rate represented by sigma dot. So sigma dot over ES plus sigma over eta d. This is another form of Maxwell equation. Both are same, just difference in the method of expression. And from here I can write, instead of gamma dot, I can what I can do, I can multiply each side of this equation with eta d. So gamma dot multiplied by eta d, here eta d sigma dot over ES plus eta d will cancel out and sigma will be there. So we got a new term, eta over ES or eta d over ES, and this is the term which defines the relaxation time. Viscosity over the modulus is the relaxation time, eta d over Es. And what is the importance of relaxation time? It tells the lower value of the relaxation time lambda is desired for faster processing of material, while lower value of lambda or relaxation time will lead to higher elastic component Es. So why lower value of relaxation time is required? Because during the polymer processing we are melting the polymer and deforming the polymer by the action or by the pressure of the extrusion machine. So during deformation, polymer will try to oppose this deformation, and relaxation time is the time after which the polymer will stop its opposition and will accept the form or the shape given by the molding system. So if the relaxation time is less, that means we can produce plastic or polymeric parts very quickly. If relaxation time is more, then we have to keep the polymer inside the mold for longer duration, means the duration above the relaxation time, so that it should accept the new form or the new change in its geometry. I hope it's clear. So in polymer processing we are always looking for lower value of relaxation time. So in order to achieve lower value of relaxation time, the elastic component should be higher and the viscous component should be lesser. Okay, and we can write this equation like this also, eta d gamma dot, and instead of this term I can write lambda sigma dot plus sigma, where lambda is your relaxation time. So these are the 2-3 different variant of Maxwell equation. Okay, the next model by another scientist, White model, is considering that the spring and dashpot both are connected in the parallel mode. This is another model. According to this model, they assumes that the spring and dashpot are connected in parallel to each other. In Maxwell model, we assume that the behavior of the polymer is represented by the combination of a spring and dashpot connected in series. White model says that the behavior of the viscoelastic polymer is represented by the spring and dashpot when they are connected in the parallel. So let's see what will happen when they are connected in the parallel. We are applying load P, and the modulus of the spring is Es and the viscosity of the dashpot is eta d. Okay, since both are connected in the parallel, so the deformation in the spring will be equal to deformation in the dashpot. That means the strain in the spring is going to be same as the strain in the dashpot. So we can say gamma is equal to gamma S is equal to gamma D. Means strain in the spring is equal to strain in the dashpot. So we can say this is the term strain. Whereas the stress in the overall model is sigma is equal to the stress in the spring plus the stress in the dashpot. In Maxwell model, which was connected in the series, stress was same because they were connected in the series, but here stresses in the overall stresses in the model sigma is going to be the sum of the stress in the spring plus dashpot. Now let us see the time deformation curve. This is the load P that was applied at time t is equal to 0, and it was applied for certain duration of time t, then load was removed, and the curve, load versus time curve, will come to the x-axis or the time axis where load is 0. Now see how is the deformation. This is a deformation versus time. So when we'll apply load P, the spring will attempt to distort immediately. Okay, because it is an elastic element, it will try to distort immediately, but the dashpot which is connected in parallel to the spring is a viscous element, and it will say no, I am not able to deform immediately, I will take some time for the deformation. So the combined deformation is a non-linear pattern like this. Otherwise viscous deformation is straight line, and the elastic deformation is the straight vertical straight line, and viscous deformation is the straight line at some particular angle. But when both of them are connected in the parallel, so the combined deformation of the model is somewhat non-linear, and it is neither at a 90 degree or nor at the angle at which this dash form is going to deform. It is between the 90 degree and the angle of the dashpot, something like this. And here at this point my load is removed. Then what will happen? Upon the removal of the load, spring will try to regain its original shape immediately, but when it will try to regain its original shape, the dashpot will present hindrance in this process, because it is connected in the parallel. It will say no, you cannot regain your shape immediately, and normally dashpot do not regain anything, but when it is connected to the spring, spring will compel or push it to regain its shape, and dashpot will compel spring not to regain its shape within no time immediately. So the ultimately you can say they will regain their shape in a time delayed manner, and this curve is going to touch the x-axis after a long time. Okay, so this is my time delayed deformation, and this is time delayed recovery. This is how White model will behave. And from equation number 1, I can write sigma s is equal to Es gamma s plus eta d gamma d dot, or we can say Es gamma s eta d, and instead of gamma d dot I can write d gamma d over dt. So this is the White model, or it is on the name of another scientist, sometimes it's known as the Kelvin-White model. So these are the two models of viscoelasticity. There are many other models given by different scientists for the viscoelasticity, but in this course we will be limiting ourselves to Maxwell model and Kelvin-White model. So I hope you have understood this viscoelasticity behavior, and I have a short video that I downloaded from the internet, and it represents it exhibits the property of viscoelasticity graphically or by animation in quite nice manner. So I am going to show you that particular animation. I hope it will make your concept much clearer. Okay, let's see this animation.
Another method of understanding a polymer's behavior is the spring and dashpot model. The spring represents the elastic behavior of the polymer. The elastic portion of the model acts as a metal and has fully recoverable strain. The dash pot represents the viscous behavior of the polymer. The viscous portion of the model acts as a fluid and has unrecoverable strain. One way to understand the spring and dash pot model is by examining the behavior of the system with a suspended load. A graph of deformation and time helps you understand the mechanics of the system. The first component of the model is a spring. When a weight is added to the spring, an immediate deformation is observed. When the weight is removed, all of the elastic deformation is recovered. The second portion of the model involves a spring and dash pot in parallel. The spring portion of the system cannot immediately deform because the viscous component slows it down. Therefore, the deformation takes place over a period of time. As the weight is removed from the system, the deformation recovery of the spring is slowed by the dash pot. The third component of the model is the dash pot. The dash pot flows while the weight is applied to the system. When the weight is removed from the system, none of the viscous component is recovered. To fully understand the model, the three components must be superimposed. When the weight is applied, the system undergoes an immediate deformation due to the spring component. The second component, with the spring and dash pot in parallel, produces a deformation over time. The viscous deformation of the third component is added to the second component. This results in a model of the behavior of the loaded system over time. When the load is removed, the initial deformation of the spring is recovered. Then the deformation of the spring and dash pot is recovered over time. The deformation of the dash pot is never recovered. The result is a permanent deformation of the system.
Okay, so we'll finish this lecture. I hope it was clear to you. Thank you for your patient hearing.